Hi, and welcome to H1.1 Rotational Motion and Angular Displacement. The H stands for honors because this is solely an honors physics topic. We do not cover rotation in the Regents Physics curriculum. In this lesson, students will be able to convert between radians, degrees, and revolutions. And students will be able to use the arc length formula to find the arc length, radius, or angle. So you might be thinking to yourself, rotation, didn't we already do that in Unit 7 when we talked about circular motion? Kind of. We did talk about uniform circular motion where we had a centripetal force that keeps an object moving in a circle. And that centripetal force was constant, which means the centripetal acceleration was constant, which causes you are accelerating, you have a change in your velocity, your tangential velocity is changing, but only the direction of that velocity is changing. The tangential speed remained constant. Well, what happens if it's not constant? What happens if you start spinning faster? All right, maybe you apply a force that's tangent to that circle. We're going to learn that that force is called a torque. It's actually not this unit, it's the second honors unit, rotational dynamics, when we start talking about rotational forces or torque. All right, but we'll get there. This is just a very broad overview, very quick, about what this rotation unit is all about. This is where we're going with it. So an unbalanced force is going to be applied to this, which causes the object to spin faster. Now we could keep looking at the tangential velocity, but that's not really going to do it for us because this is like a particle, right? We're going to have other objects. Maybe it's a rod that spins on an axis, or maybe it's the planet Earth. The whole Earth is spinning, and we have a sphere that we're analyzing. So it's not just a particle. We have to think of like the spinness of it, right? Not just the tangential velocity at a certain point, but the whole object spinning through an angle. All right, that angle is how we're going to define how fast it spins. The tangential speed increases, it completes more rotations per second, right? So speaking of that angle, 360 degrees or 1 revolution or 2 pi radians. You might have heard radians in your math class before. We're going to use radians in this unit. So we're going to use that to define the speed, how fast, how many rotations per second, instead of how many meters per second tangent to your radius. All right, so it's a very slight difference there. So yeah, we have this angle that we're going through. That's how we're going to describe the displacement. It's called your angular displacement, which leads to your angular velocity. Because we're applying a force and making you go faster, your angular velocity increases. Basically, you're spinning faster due to a constant angular acceleration. Well, why did you accelerate? Newton's second law. You must have some kind of force. That force is called the torque. So this is applied force causing a rotation is called torque. And you could go faster. So that's a very brief overview. You might have some questions, and we will answer a lot of them as we go through this unit, rotational kinematics, and the next unit, rotational dynamics. But I wanted to give this brief overview to show the difference between the concepts we learned about in circular motion and what's coming up in this rotation unit. So a lot of the rotation unit just has to do with, okay, we learned about the linear physical quantity, and then there's a correlation to this rotational physical quantity. So instead of displacement, we're talking about angular displacement. And instead of using a d, or actually when we talk about arc length, s, all right, that's your almost like your linear displacement. We're going to use theta. What is your angle? The angle that you rotate through. And instead of meters, we're going to use radians. That radians is the SI unit for angular displacement. And this comparison goes through the unit. So instead of v for velocity, we have the Greek letter omega for angular velocity. Instead of a for acceleration, we have the Greek letter alpha for angular acceleration. And luckily, time is the same. And then in the next unit, H2, rotational dynamics, instead of force, we have the Greek letter tau for torque. And instead of mass, we're going to talk about the moment of inertia, I. And inertia, mass, that should ring some bells there, right? So when we have different objects, maybe it's a rod that's rotating through its axis. All right, it's going to have the mass is going to behave differently than if you rotate through one end of the rod, right? So how do you account for the mass distribution of the object? It's called the moment of inertia. And then we have Newton's second law here. So F is equal to ma. Well, if we use our Greek letters here, instead of F we have tau, and instead of m we have I for the moment of inertia. And if you remember in the previous slide, it said instead of a we had alpha. So tau is equal to I alpha is the equivalent of Newton's second law. And we're going to get there in the next unit. But let's start by just talking about angular displacement. So let's start this unit like we started mechanics by discussing displacement. This should look familiar. This is kind of what we did in the beginning of the year. What's the total distance traveled? What's your total displacement? But instead of a straight line, we need a way to describe how far we traveled around a circle. In other words, how many degrees around an axis did we travel? So let's kind of like redefine what displacement is in terms of this rotation idea. So angular displacement, and instead of a d, we're going to use the Greek letter theta, which should make sense because we're talking about an angle, and we always use theta for the angle. So the definition of angular displacement is the angle through which a rigid object rotates about a fixed axis. Angular displacement is a vector quantity. What does vector mean? It means it has a magnitude and a direction, a size and a direction. So this is what it looks like. Let's say you start here and then you rotate this way there. All right, so what is your angular displacement? How many degrees did you rotate around? And it could be just part of one revolution, it could be a full revolution, or you could have multiple revolutions traveling around and around and around. You could still measure how many degrees that is. But it doesn't have to be degrees. You could say how many revolutions is it, or how many radians is it? Okay, so let's see. Oh, and by the way, look at this. I made a direction. I made an arrow. So what are our units for angular displacement? You kind of have a choice. You could use degrees, you could use revolutions, but the SI unit for angular displacement is radians. Radians. So the direction, by convention, if you're looking from the top down, so here's your eye, and in this case we're looking from the top down here, and we're rotating this way. All right, would you say that's clockwise or counterclockwise? I would say that is counterclockwise, which we're going to call positive. So the way to remember this is what they call the right-hand rule. So this is kind of getting ahead of ourselves, but it is a good thing to do. You put your knuckle here and point your fingertips here, and then your thumb points towards the direction, and you give a thumbs up. So it should look like this. That is horrible, but hopefully you see you have the thumb up there and your fingers are pointing in the direction that you're rotating around. We said in this case we're going this way, and if you do it at home, all right, if you curl your fingers around that, you're giving yourself a thumbs up. So that's counterclockwise. And if you wanted to do the same thing, let's say now we're rotating this way, you put kind of like your knuckles here and your fingertips are pointing over here now, and you have to turn your hand upside down, and now you're giving a thumbs down, like, wow, Mr. Nangle's really bad at drawing hands. Thumbs down for Mr. Nangle. All right. But all you have to do is remember, clockwise is negative, counterclockwise is positive. So anyway, how many of each unit equals one complete rotation? Think about it. How many degrees is one complete rotation? 360 degrees. And how many revolutions is one complete rotation? One revolution. And do you know how many radians in terms of pi is one complete rotation? Do you know? Is 2 pi radians is one rotation. And if you were going to give that answer in like decimal form, if you didn't want it in terms of pi, all you have to do in your calculator is just 2 times pi, or 2 times 3.14, which gives you 6.28. So you can express your answer in terms of pi, or if you want to do the multiplication out, 2 times pi, 6.28. That's for one revolution, right? So how would you convert these? All right, if you want, you could pause the video and try to do the conversion. So the way I do it, I always do these the same way. I write the thing that I want to convert, then I set up my parentheses, and I had degrees in the numerator here, and I want degrees to cancel out. So I put it on the bottom, and I put radians on the top. So how many of one thing is equal to the other? 360 degrees is equal to 2 pi radians. All right, so that's kind of like the conversion factor. So then the degrees cancel out, and you do 90 times 2 pi, so that's 180 pi, divided by, this is like 1 times 360, 360, so you get pi over 2. Which you might have memorized. 90 degrees is equal to pi over 2, but just so you know, that's where it comes from. So that's kind of nice there. And then if we wanted to convert 3.5 revolutions into radians, it's the same process. You write the number down with its units, please. Then you multiply by some parentheses. Put a line in the middle, because we're about to make a fraction. So the revolutions, write the unit that you just wrote on the opposite side so that they cancel out. And then you want to convert into radians. Okay, and then how many of one thing is equal to the other? We don't want to actually change the magnitude of this number. We want to effectively multiply by 1. And 2 pi radians is equivalent to 1 revolution. So this magnitude is the same as this magnitude, and when you divide them out, the magnitude of this whole fraction, when you divide the same number divided by itself, it's equal to 1. So we're not actually changing the size of the number, but just so you know how this all works. The point is so that the units cancel out, and then you do 3.5 times 2 pi, and that leaves you with 7 pi radians. And you could leave it just like that. That's totally fine. Or you could, in your calculator, you could multiply it out, and that's totally fine too. All right, then we want to convert the other way, 1 radian into revolutions. So you just write the number that they're giving you, 1 radian, and you multiply by some parentheses. It's the same process every time, okay? We want this to cancel out, so we'll put it on the opposite side, and we want to go into revolutions. And then you ask yourself, okay, how many of one thing is equal to the other? 1 revolution is equal to 2 pi radians. That's something you're going to have to memorize if you don't know it by now, that, 2 pi radians is equal to 1 complete rotation. So let's see how we do. Cross that out, and then you're left with 1 times 1, so 1 over 2 pi revolutions. That's fine, but in case you're wondering, that's equal to 0.1592 revolutions, or about 0.16 revolutions. All right, so 0.16 of a revolution. 16 hundredths. So yeah, where the heck does that 2 pi come from, Mr. Nangle? Why is it 2 pi? Well, it comes from the definition of a radian, which the fancy definition says a unit of angular measurement that is equal to the angle at the center of a circle subtended by an arc whose length equals the radius, or approximately 57.3 degrees. Let's see what we could do with that. The angle subtended by an arc, this is the arc, and the length of this arc in meters is equal to the radius. All right, that is considered 1 radian when the arc is equal to the radius. Why, Mr. Nangle? Why is that even a thing? It's just a way to define the angle based on the arc length that the angle sweeps out and the radius of the arc. So instead of using degrees or revolutions, we're using the geometry of the circle to define the angle, which is useful. So this is the arc length formula, which states that the angle is equal to a ratio of the arc length in meters. How long is that arc length? Divided by the radius. So this is the arc length here, and this is the radius here. Okay, when you're using this formula, the theta needs to be in radians. So here we go. And what happens? What happens? We said that the arc length is measured in meters and the radius is measured in meters. So what happens is those units cancel out, which is like how the radian is defined. We're just using the geometry of the circle, the radius and the arc length, to define how much of a rotation did you do. Okay, so how many radians is 1 revolution? This is like from the previous slide when we were doing those conversions, and I said, well, it's just 1 revolution is equal to 2 pi radians. Here's why. We're going to use this formula, okay? So if we're talking about this formula here, and we're talking about the arc length, and we want 1 complete revolution, well, that arc length for 1 complete revolution is a full circle. What is the distance around 1 circle? This is the circumference. So in our example that we want to do, where we're saying, okay, for now we'll just say 1 revolution, even though you should use radians when doing this. But by definition, 1 revolution, 1 complete revolution is equal to your circumference, because again, the arc length for 1 revolution is the distance around the circle. So C is equal to pi d, or 2 pi r. And then following the formula here, we have the circumference, the arc length, divided by the radius. Okay, and what happens in our formula? The radius cancels out, and by definition, using our arc length formula, we see that 1 revolution is equal to 2 pi radians. So that's kind of where the 2 pi comes from, in a nutshell. Just remember, I plugged in a revolution over here just to kind of show you where 2 pi comes from. But whenever you're using this formula, you have to make sure that the angle that you're putting in is in radians. You wouldn't plug in revolutions over here. All right, so I don't want to confuse it like that. Again, I'm just showing you where this conversion factor kind of comes from in a nutshell. So, where is the arc length formula in your reference table? Well, as we stated, this is not a Regents topic. This is not covered on the New York State Regents. So we need to amend our reference table a little bit. And I created page 7 of the reference table, rotation. So where is the arc length formula in this reference table? It's actually right over here. It looks a little bit different, but S is equal to R theta. All right, so this is, we're going to get into, S is like kind of like the linear displacement. If you think about the distance around a circle measured in meters. All right, so the way to go from angular displacement to linear is you just multiply by the radius. And when we do angular velocity, if we wanted to convert that into tangential velocity, again, you multiply that by the radius. Same with the angular acceleration and the tangential acceleration, you just multiply by the radius. So those are all over here, and that's the reason why it's in this form instead of theta is equal to S over R, but either way is fine. Please note that for these formulas, which should look familiar, hopefully, does that look somewhat familiar? The units must agree. So yeah, you could have revolutions as long as everything's in terms of revolutions and revolutions per second. But you wouldn't put in like radians here and then revolutions per second here. You'd want it to be agreeing with either all radians or all revolutions. And then for all of these formulas here, it has to be in radians when you plug in either an angle here or a radian per second or a radian per second squared for the angular acceleration, and so on. It has to be in radians. You cannot plug in revolutions or degrees like that. So we'll finish with two examples, or an example and a practice problem. So it says synchronous satellites are put into an orbit whose radius is 4.23 times 10 to the 7 meters. So that's this radius right here. And if the angular separation of the satellites is 2 degrees, find the arc length that separates them. If you want, you could try to pause the video and try this one out on your own. So the first thing I would always do is write my given information. The radius is 4.23 times 10 to the 7 meters. They're telling us 2 degrees. The angular separation, the angle is 2 degrees. And we want to know what the arc length is. That's S. Okay. So we would like to do, maybe theta is equal to S over R, or if you look in the reference table, S is equal to R theta. So we would like to plug in like this, but what's wrong with this picture here? This is in 2 degrees. We need this to be in radians first. So you cannot plug it in like that. We have to convert into radians first. And the way to do that, you just multiply by some parentheses, put the degrees on the bottom so that they cancel out. We want to go into radians, and we know that 2 pi radians is equal to 360 degrees. So the degrees will cancel out. You're left with 4 pi over 360, or pi over 90 radians, which you could also express as 0.0349 radians if you wanted to do the division. Pi divided by 90 is equal to this, 0.0349. So you plug either one of those values in for the angle, and you get an arc length of 1.48 times 10 to the 6 meters. That's this distance. That's how far apart they are. That's pretty far. How far in miles is that, I wonder? Well, there's about 1609 meters in 1 mile. So when you do the division, 1.48 times 10 to the 6 divided by 1609, you get about 920 miles. A little less than that, 918, something like that. Okay, so that's pretty far apart. Right? Nice. All right, so key there is make sure that your angle is in radians when using the arc length formula. Don't forget. All right, so this is kind of like a critical thinking one. You can practice this on your own if you want. It says, what is the angular displacement of the hour hand, minute hand, and second hand of a 12-hour wristwatch over the course of a day, or 24 hours? And I want you to give your answer in terms of radians. So it's like 3 separate problems in one. How many radians does an hour hand go through in 24 hours? How many radians does a minute hand go through in 24 hours? And how many radians does a second hand go through in 24 hours? This is a classic critical thinking problem. So if you think about your hour hand, and if it's a 12-hour wristwatch, it has to go all the way around once, that's 12 hours, and then around again, that's 24 hours. So how would you express this 2 revolutions in 24 hours? So for the hour hand, we can think of, okay, well, how many hours is 1 revolution equal to? To go around once, it takes 12 hours. So that's like a conversion factor right there. 1 revolution is equal to 12 hours. So 1 revolution is equivalent to 12 hours, right? So let's use that knowledge to do a little conversion. If we had 24 hours and we wanted to convert that into radians by the hour hand, well, we have 1 revolution per 12 hours, and we want to convert into radians. So again, we have revolutions in the numerator. We put that in the denominator, radians right there. 1 revolution is equal to 2 pi radians. So it's like we're doing 2 conversions at once, so that the hours cancel out, the revolutions cancel out, and we're left with radians. So we have 24 times 1 times 2 pi divided by 12 times 1, or just 12. So 24 times 2 is 48 pi divided by 12. That'll give you 4 pi radians, which if we were going to check ourselves, kind of makes sense because we predicted, okay, this should go around once, that's 2 pi for 12 hours, and then twice, that is 4 pi, 2 pi times 2, for 24 hours. So that's the process I like to do to solve this problem. If you want, you can do some critical thinking for the minute hand and the second hand now. All right, so if you want, pause the video. And we want to think about, okay, there's this minute hand here. How many hours does it take to go around once? So the minute hand goes around once every hour. The minute hand goes around once every hour, right? So if it's a 24-hour period, then it would go around 24 times. And here's how I would show that in math. We have a conversion factor. 1 revolution of the minute hand is equivalent to 1 hour. And then we want to know how many radians is 24 hours for the minute hand. So we do 1 revolution for the minute hand is equal to 1 hour. And then similar to before, we want to get out of revolutions. So we go into radians. 1 revolution is equal to 2 pi radians. So now we have 24 times 1 times 2 pi, again 48 pi divided by 1, and we're left with radians. So this is equal to 48 pi radians. Okay? See if you could do it for the second hand. First of all, how many hours is equivalent to 1 rotation of the second hand? Or you could think of it differently if you want. So pause the video. How would you define 1 rotation, 1 complete revolution of the second hand? How would you define that? Okay, you might say, well, the second hand goes around once every minute. So you could use that. 1 revolution is equal to 1 minute. Now, if you do it this way, we're going to have to add another term when we're doing our unit conversion, but let's see what that looks like. Again, pause the video here and see if you could try it out on your own. So we're setting it up. We said that 1 revolution is equivalent to 1 minute for a second hand, right? And we want to know how many revolutions is in a 24-hour period in terms of radians. So first, let's get out of minutes. So we know that we want to put the minutes on the opposite side here so that they cancel out. And we want to go into hours. 60 minutes is equivalent to 1 hour. So let's see what we're doing here. So far, the hours will cancel out with these hours because they're on opposite sides of the fraction. And the minutes will cancel out with the minutes, but we still are in terms of revolutions. So we have to cancel out those revolutions and make them radians instead. So 1 revolution is equivalent to 2 pi radians. And again, I put the revolutions on the bottom because they were on the top over here, and we're going to be left with radians. If we do 24 times 1 times 60 times 2 pi, and then divide it by 1, so you're left with 2,880 pi radians. That's a lot. It goes through many rotations. The second hand goes through many rotations in a 24-hour period. The minute hand goes through less rotations in a 24-hour period, and the hour hand moves very slowly. It's going through the least amount of rotations in the 24-hour period. Now, we're dealing with time here, which is kind of getting into the idea of angular velocity. How much angular distance did you go through in a certain amount of time? But I did want to just show how to A, convert between units, but then also B, thinking about, well, what happens if it's not just one rotation, but multiple rotations? Kind of how do you handle that? So try out the homework. Thanks for watching and have a great day.